Okay, so finish the registration and also the pavement of that is finished. 大家注册都完整了，那个单据什么都有了。单据这个要件主任还没有。OK， 好，那我们再等一下。OK， so next will be we need to have the insurance. So remember, I'm not sure if they already collect the insurance. Okay. Yeah, so we will have the insurance, and then we will take HSR to there. And I'm trying to find a budget to cover the HSR ticket. So after I confirm, I will let you know if we can cover all of your HSR ticket, and then you just pay the registration fee. Okay, like that. Okay. Let's continue. So this part try to address that the hydrogeology or the geology is very important for the study, like even the earthquake issues. And following will be discussing the system, why they become consistent of the ground levels, and what could be the disturbances for the aquifer system. And in the past, Professor Shih-Jung Wang, he proposed that there will be we call it enhanced permeabilities. That means that the aquifer system might be damaged and that the aquifer system totally connected. So we might be able to see that the ground level become the same or consistent like these kind of patterns. Originally, before earthquake, they are separated. But after earthquake events, some of the wells seems to be connected, and they call that a permeability enhancement. Or they could be, we can also say that it's kind of damage processes. When the aquifer system have the damage, they might have the connections between because they might not have significant aquifer to seal the system. But another difficulty is that there could be the device problems, or there could be the setting problem. It's not exactly aquifer damage. Because if you know the well settings, commonly in this kind of wells, we drilling relatively big wells. Okay, we drilling original big wells, and we put several small wells, and then we seal the system. Okay, like that. So this wells, this screen observed this system, and this one observed this system. So that's the original concept. But when earthquake happens, earthquake can damage the outside aquifer system, but it can also damage your well system. Okay. So if the original seal system be damaged, maybe the waters become connected in the wells, it's not outside the well. Okay. So that could be the system damage, not the aquifer damage. Okay. So we cannot avoid this kind of behaviors due to this kind of system damage. Okay. So another important concept is that when you take the data to do the work, always you need to think about, or you need to check if the data quality is good or not, or how the data obtained. Sometimes the data obtained, they have some of the steps, but if you do not think carefully, you might misunderstanding some of the explanations. For example, in the previous dimensions, we go back to this. Okay. Do you know how they measure the river flow? You also need to know how they measure the river flow, so you will be able to explain what could be the possibility to induce this kind of anomaly. I don't know how to draw it clearly. It's not easy to draw that. This is the river we use in the cross section, the river flow this direction. Okay, and commonly we set up the device on the bridge. This is the bridge human can pass through, and we're using the like a kind of camera, but it's not exactly camera. That's the 红外线. I don't know how to say English. They're using some light to detect the river surface. So when your river surface increase or decrease, they using this kind of traveling time to inverse the level increase or decrease. And after that, they're using that to calculate the discharge quantities. So that means they're using the elevation to calculate the discharge. And they assume this one is the constant. So commonly, they need to do the corrections. There will be a regression curve to do the corrections. Okay. So if you know this, when earthquake happen, you need to be careful. For example, your bridge might damage. Okay. So if your bridge damage, they become decline. This one moving down. That means this system, they will observe the ground level uplift, the surface water uplift. So you will gather the increase of the water levels, okay? If the bridge down. And another could be the channels, river channel. If you ever go to the river channel, especially in Taiwan, the river channel is not always full of waters, okay? Sometimes they might have some of the same. So they become, this one is the river, this is the river channel. So in some of the earthquake happens, damage, they might uplift the river bed. They might, like this become, and water is only flow these directions. Or they uplift your river bed, so your water also uplift a little bit. So what you see, what you observed, the river levels might not be totally correct, okay? So this one also have the uncertainty. But one of the possibility you can take a look is that if they go back to the original level or not. If they go back, maybe still the data still reliable, because that means they might just disturbances to let the water uplift and then they go back. But if you see the permanent changes quantities, it might imply that your bridge or your system be disturbed. Okay. So the data might not be totally correct. Okay, so always remember that when you gather the data, be careful for the data quality. And the same like geology or hydrogeology, you gather the data, totally not able to directly use. But honestly speaking, sometimes we are not able to judge if the data quality is good or not. So commonly just gather the data and use the data. But you also need to understand that sometimes they still have uncertainty. So in Professor Dong's lab, commonly they will try to take a look carefully for the original data, like geological data, to reclassify or to read the materials, and then they can recognize the really correct or match the reality, more match the reality result. But from our lab, we are not able to do that work, so we just using the data. So sometimes it's not easy to control the quality. Yeah, so that's just reminding you that when you're using the data, be careful. Okay, so yeah, this one is they using we call tidal analysis to analyze before earthquake and after earthquake if the groundwater level signals have the change quantity or not. Because tidal signals, that means the barometric pressure or like gravity influences for your earth tide. They will have the water to flow in the wells and flow out the wells when you have the balance stream. We call the earth tide. Earth tide means that we know the sea tide is affected by moon. So moon also affects barometric pressure, also affect the solid earth. Okay. So for the solid earth, we call it earth tide. For the barometric pressure, we call it barometric tide. Although the contribution might not be significant, so commonly using the sea tide. And this kind of concepts they use in the earth tide. But that means that your earth tide signal need to be significant enough, and then you will be able to use in this tidal. The earth tide concept is that when your earth have the expand or compress due to the gravity of the moon, you have the valence stream. And this valence stream will induce the water flow in or flow out to the wells. Okay. So they can use in the theoretical earth tide valence stream and your observed groundwater level response to calculate the time lag. and they're using the time lag to inverse the transmissivity or the permeabilities. Okay, they're using this kind of concept to do the inverse. So they were able to gather the differences. So before the earthquake, they might have a patterns, and after earthquake, they might have another patterns. So they can use these kind of differences to see if the permeability affected by the system or not. Okay, the concept like that. But the detail, I think we do not have time, so I'll skip this part. You just memorize that they were using the time differences. Okay. And we can use that to do the quantification for the why they have this kind of differences. And another part I forgot to mark together for the liquefaction. Here is the liquefaction point, the yellow colored circle. Okay, this is the liquefaction point. So we can see a lot of liquefactions in this area. And also mentions that this have the river discharge increase. We also have a liquefaction point. Okay. And liquefaction point, that will be one of the important concepts. I hope you can also memorize that. How to define liquefaction point. How we define liquefactions. Okay, that's a very important concept. For example, we go to the field to take a look at the liquefaction point. We found, oh, there's the liquefaction, several points there. And the other place, we do not have the liquefaction point. So we will define that this is liquefaction area, and that is not. Right? Be careful, it's not correct. Okay. What we define liquefactions is what we see the liquefaction. Okay. But sometimes liquefaction happen, but they do not erupt to the surface. So we do not see that. So when we define liquefactions, what we observe on the surface, but that means only this place have the liquefaction. Some places do not have. No, not like that. So in the sedimentologists, you might ever see some of the, I forgot exactly the term, they describing the sediment concept. Okay. Original the system may be like this, but when some of the situation, or this one could be sealed or the fine sand, okay, maybe fine sand, okay, seal or sand. When some of the earthquake triggerings, they might let this area become liquefied, and they will induce the increased water pressure, right? And they need to try to find a place to escape or to decrease the water pressure, high water pressures. So they might induce this kind of shape, or sometimes they become like this kind of shape. So I forgot exactly the term. I don't know if you remember. In the sedimentology system, sometimes you can see this kind of shape in the sediment. And this kind of shape is induced by like a liquefaction phenomena. But this one, they do not erupt to the surface. They will be sealed. Okay. So these behaviors also occurred in a lot of the sediment system. So I want to emphasize that liquefactions is not what we only see these kind of places. Liquefactions can be much larger, widely distributed. But we only see is the open channels of the liquefaction erupt. Okay. So a lot of places you might be able to see, as I mentioned, that they have this one is the Xinhua fault trace. If they have the surface damage, surface rupture areas, you will commonly see the liquefaction occurred. But that means that they have the open channel to let the excess water pressure dissipate. So you'll see the liquefactions in that area. But in some of the places, as I mentioned, in the Jiangnan Plain, they have a lot of clay layers. So they become the seal system. Even you have the liquefaction occurred, balance that, you were not able to see the eruptions. So you will imagine, oh, they do not have liquefaction. It's not totally correct. Okay, so be careful for these issues. So another is that some of the professors, they were using like a building tilt, or some of the, like they become the deformation, surface deformations. They define as liquefaction, but some of the geotechnicians, they will mention, oh, this is not liquefaction, it's just deformation. Okay, So if you see like this kind of uplift, you might see the surface also have the uplift behavior, or you will see the buildings tilt. So they might imply below that they might have liquefaction occurred. Okay. So that professor, what he talked, I agree with that. He already retired. I forgot exactly the name. Huang Fuguo. Yeah, a professor. He just retired. He proposed that. So when he tried to do the liquefaction survey, he will mark a lot of points. Okay, but for the GSMMA people, they go there. They say, oh, there's not. Okay, they delete. They only mark the eruption point to be the liquefactions. Okay, so the concept would be different. But I'm speaking, I hope you can understand that liquefaction is not just what we see, and we can define liquefaction. Sometimes it's not. They imply that in this area, they might have the regions have the liquefactions, not only a point or a small area. It could be very large, but just one open channel to let the exist water pressure erupt. Okay. Okay, and here's some of the discussion for the damage. I escaped this part. Okay, and here we go to the motions part. So as I mentioned, that ground motions is one of the important components, like the driving force to triggering the earthquake hydrology response. And commonly we use in the PGA. It means peak ground acceleration, and PGV is peak ground velocity. That means we have the acceleration signals, and we find out the maximum point. That quantities we call the PGA. Okay, so each station we will have one PGA, and each station will have the PGV. We can do the integrations to become from acceleration to velocity. We can have the velocity field, and we can also get the maximum point to have the PGV. And there's horizontal. That means we combine the north, west, and southeast. Yeah, like that. So we try to combine the components together to be the horizontal PGA and PGV. And commonly we use in the PGA, but you can take to the PGA distributions. This is epicenters 1, 2 missing. Okay, this around 2 here. Okay, so the PGA distributed here more stronger, so they might be more consistent with the earthquake epicenter number 2. Okay. But when we take a look at the response with the ground level and liquefaction point, we will find that they seem not consistent. We can imagine that commonly when the energy is stronger in the place, we might able to see more damage or more response for something. Okay, but the ground level is not consistent with the PGA. But when we compare to the PGV, they look more consistent. Okay, so you can see that almost high response is around the high PGV system. Okay. Although when we try to do the correlation, it's not easy, but the patterns look more consistent compared to the PGA. And this is enlarged Ramin content. So it implies that the ground level response seems more affected by the peak ground velocity, not the accelerations. But that could be two ways, as I mentioned. One of that is the wave is the mainly triggering the velocity mainly triggering the water level response. And the second is that this area have the liquefaction or have the more water response. So they soft the material to let your records on the surface become weak. Because the ground motions detect on the ground surface. Okay. So it need to penetrate, the wave need to penetrate the aquifer system. So if this area, they have the high water pressures increase, they might become like a soft material, and they might attenuate or let your energy become more weak. And another could be they will feel the high frequency, because we know liquid is not able to bearing shear wave. Okay. So they will dampen the high frequency and only keep the low frequency. And so there could be another possibility that when we observe the PGV here is high, it's also due to the material be affected. So they have interactions, not just one way, not one affect another. Like wave influences ground levels. ground level also influences the wave. Okay, so they become interactions, not easy just to have one way. But from the comparisons, the ground level response will be more consistent with the PGV concept. And that could be very important because in the building design, commonly we use in the PGA, not using PGV. Okay, so but this one is ground level response. It's not the buildings. Okay, yeah, just for your reference. So we try to do some comparison and try to find out the threshold. Like this is the happens more high ground level response has the PGV and PGA. We try to find the threshold to triggering larger ground level response. Okay, so let's try to do the quantification. And also the question, we try to read the PGA and PGV quantities, and that could be the threshold to induce the largest liquefaction events. So try to find out the threshold for PGA and PGV. Okay, and another, we try to take a look at the displacement field. That could be the horizontal displacement and vertical displacement, because they can use in the INSAR system to detect the deformations. But the same, we can see there's an increase of the surface, but some of the press, as I mentioned, they have the increased water pressure, but some press have decreased. This one is just compared with the first layers, but we know that in this press, they also have the decreased ground level. And horizontal displacement the same, they are not seems quite consistent, but they have some connected. Not completely, but they have some connected. Okay, so this press, we have more damage of the fracture system or the values. So they have another colors for the values. Okay. Yeah, so like that. And ground level response with the equator may be not easy to connect. But like ground level response, they might imply the sensitivity of the aquifer system to the earthquake events. So right now, you're trying to do that for the whole Taiwan area. We try to use in more earthquake events to understand the whole Taiwan ground level response to the earthquake events. Okay, so this is just one example. And conclusion, I also escaped. I think most important part is that in this study, we try to address that hydrogeology plays a very important role. We cannot just use in the empirical concept or just using the regression concept to do a lot of analysis. We need to consider the hydrogeology or geology concept. And we need to even consider the topography inferences. Okay. It is not only the distance. If you use the distance, that means you ignore the other inferences. Like I mentioned, the rock system and the sediment system, you cannot combine them together for the comparison. It's not correct. Okay, and next the topic is about lens subsidence issues. For lens subsidence issues, we do quite many. So several students do this kind of work. And this topic is done by Ms. Yang. The title is the inferences of geological models with different complexity on lens subsidence simulations based on a coupled hydromechanical model, a case study in Yunlin County. So we try to discussing how the differences of the geological models affect lens subsidence assessment. Okay, we have several topics talking about this, and this is one of them. We know that subsidence is very significant in the Joshua River VFN. And one of the interesting parts is that subsidence in the past is mainly occurred in the coastal area near the sea waters. But recently, the centrals move inland. So what could be the reasons why they have this kind of shift patterns? So that could be very interesting. Yeah, some of the professors proposed that, yeah, this one is the historical subsidence because they pump a lot of waters in that area for the aquaculture activities. So after a period of time, the clay compress or become like a permanent displacement. They reach the steady state condition, reach the final compressions. So they stop compress anymore. And right now, the new pumpings occurred inlet, so we can see the continuous pumpings here. Okay, so they proposed this concept. but is that really correct or not? Or we shift the pumping like a subsidence the same. Always we have two. Okay, one is the intrinsic properties, if they are sensitive for the subsidence, and the second is the driving force, the pumping change or not. Okay, pumping is the driving force. They decrease the water ground level and reduce the compressions. Okay, so if the system did not change, and we just imagine that, oh, if the pumping originally here, so right now they move to the inlet and this one stop pumping, so they become like that. That could be correct. But honestly speaking, this area, they still have some pumping activity. Although if the pumping changed largely or not, it's not easy to control because we do not have the pumping observation or pumping quantities for this kind of work. Okay, and another could be is that due to some of the geological issues, hydrogeological issues to induce this kind of the pattern changes. So in this study, we can demonstrate that hydrogeology could be one of the possibility to induce this kind of shift. Okay, so originally we using a layer system like this kind of aquifer-equator system, as we mentioned previously. This is a relative ideal case. Okay, but for the previous part, we know that it's not really look like that. And in the past, also a lot of researchers published the covering system they using like ideal conditions, layer system, very perfect layer condition to do the assessment. So right now we try to discussing when we have the different kind of geological systems, and when we use the covering system, what could be the result look like? Here is the profile that we in the study area. So from the profile, we can see that they have very larger differences for the materials from the gravel to the mud. Okay, so that's very commonly sought in Taiwan. And from the GSMMA, they already defined this kind of model, although I am not totally agreed with this model. But right now, we try to use this model first and try to use the model for the simulations to see how it affected for the land subsidence. Because for the Water Resource Agency in the past, they only using the aquifer and equator, as I mentioned previously. They only using this two kinds of the system and related ideal cases, aquifer equator system. They do not have the lengths, or they do not have the segments. They just continuously to have aquifer and equator. But commonly for the systems, they are not. They will be relative compressed, like this kind of river channels. You can see that they might have some of the additional river channels, and the deposit will become more heterogeneous. They will not uniform have the layer system. Okay, they could be like a discrete materials there. So in this work, Yonghan do a lot of system, but we just focusing on the small part. I use that for the presentation. So I using model in situ model 3 and 4, and using the scenario 3 for the analysis. But if you would like to see more completely, you can read his thesis. It's more complete. And then we're discussing the geological model inferences and also the dependent parameter inferences. Here's the governing equation. We're using a polar electricity. So since this is not so important in this class, we escape this part. We're just using a couple. You just know that we're using a couple system to solve the displacement and water pressure at the same time, and we can have the groundwater and also the displacement or deformations. And dependent parameter means that we try to assess when the compression occurred. The Varron strength will further influences your porosity, and further influences your permeability and Young's modulus, or your rigidity. So it will become iterative, not only just the constant values. And the study area is unique, so we select the profile from the coastal area to the inland. And this is the profile that we obtained from GSMMA. And in this study, we try to select this domain, okay, to do the assessment for the land subsidence. And this model is the WIA models. So as I mentioned, WIA model, they try commonly separate to two kinds of material, only the aquifer and equator systems. Okay, relative ideal case. But this model is based on this model. So you can do the comparison. This one is the same, right? This one is the same. They become more continuous, and this one is the continuous, this one continuous. But they ignore another segment, like you can see that. All of that is ignored. So we try to do a comparison. If we're using this kind of model and using these simplified models, what the subsidence look like, how this kind of geological system affect your simulation result. Okay, in the past, we only using this to do the assessment. For the water resources, it's okay, but for then subsidence, this one might not be okay. So we have these two models, okay, simplified model and the complex model. We call the WA model and GSMMA model, like that. And this one, we have 4 kinds of material. And this one, we have 2 kinds. And as I remember, aquifer seems to use in a coarse sand, and aquitine using clay, like that. Okay, parameter setting with escape. Okay, that's the boundary setting escape. So the driving force in these models, we use in the uniform, the same decline of the head. We do not use in the pumpings. We use in the head to control the pumping's conditions. We know that if we like to assess more completely, we might use in the pumpings, and then pumping induce the decrease of water level, and water level decrease induce the compressions. Okay, but right now we don't know exactly the pumping quantity, so we try to avoid the pumping settings. We directly jump into the ground levels. We know the ground level observations, right? So we directly assess this ground level decline or uplift, how it affects the system. So that's the concept. And from the original observations, this is the background oscillations of the ground level for 1970 to 2010. And from this pattern, we can see that although right now the ground level variation is quite stable for a long time, for maybe 20 or to 30 years, stable. But in the past, it is relatively high. And right now, they have the drainage lower than 15 meters. Okay, so this is the main driving force. Okay, they decrease the water level. And this issue is sometimes not easy to explain much. They look like we call it pre-consolidation head. Pre-consolidation head concept. So in the past, they are relative high level, but right now they are relative low levels. So although right now we see the ground level is stable, but for the clay system, they will continue to have the drainage behaviors, because they need to let your system match another equilibrium. But the clay drainage is very, very slowly. So if you would like to let the system reach the steady state condition, it takes hundreds of years, even thousands of years. Okay, so even we have 15 meters decline, the aquifer system is stable, but the aquitine system is not stable. And that's the main reason we can see the compactions continuously. Okay. And here's the simulation, here's the initial setting result. Since the setting is similar, so the condition is similar. And one of the important things is the head and pressures is different concept. Head, as we mentioned, that head means they are the driving force. High head to the low head. That means the water flow from right to the left. Okay. But the pressures, we can see the bottom is high, shallow is lower. They are not imply the water flow this direction. No. Okay. Pressures is relative to the depth, the water depth. It's not the driving force for the waters to flow. As you have the bottle of the waters, we can imagine the bottom of the bottle have the high pressures, but the water inside do not have the flow, right? So they become relative steady state conditions. So remember that water pressures is not the driving force for your water flow, and head will be the driving force. And we mentioned that head include the pressure head and elevation head. Okay, I hope you can remember that. And the displacement we set up initially to be 0, so I think that's we do not spend much time here. We just take a look at how it affected the result. And in the stage, the hydraulic head change is very step changes, but your variance change or vertical displacement, they will have initially change, but they will have the gradually change, okay? They have the lag behavior, and the lag is due to the geologic processes. As we know, the quantum flow is, quantum K is very small, so the geology take much more time. And here's the simulation. Okay, so this is the WIA models. So WIA models, maybe you can take a look at the variance stream first. When we have the quantum level decline, all of the systems have the same quantum level decline, aquifer system, okay? And we can see the variance stream occurred from the boundaries and go to the inlet. Go to the inside, okay, not inlet, okay, go to the inside. So that means the drainage occurred from the boundary of the clay. This is clay, okay, clay layers. So the drainage and then be compressed, and then gradually be compressed totally. So they will have reach the permanent deformation. So this is the variance stream. And the quantum levels, we can see not a larger differences, although we have the decrease because originally it's relative high, and then we have decreased 15 meters. And then let it persist for the long period of time. Okay, so this is the quantum level decline. And this is subsidence. Subsidence means that we are only considering the surface displacement, okay? The others accumulate together. So we can see that in this system, the significant subsidence only occurred here. Although this one have slightly subsidence, but do not have significant, but we can see largely subsidence only occurred in this area. Okay, and they're also very easy because the equatorial system here is relatively thick. Subsidence is mainly occurred from clay material because they are relatively soft. So when you have the decline of the head, your clay thickness will mainly control to your compaction or subsidence. So you can see clearly this one is this one is more thick. So this area will have larger subsidence quantities in this area. Okay, match our expectation. And this one is the GSMMA models, is more complex model. And the same, we can see that the major compressions will occur in the clay material, but they still have the fine sand or other material. So they will have their different contributions. But after the clay distributed more match the realities, you might see the pattern will be a little differences. For the thin clay material, they will change faster, so they are easy to be compressed. But for the thick material, clay materials, they take much more time to change. So they will have more significant delay, the patterns, okay? And quantum level the same, that aquifer system have a decline of the head. Okay, so they have the head decline, and we can see the dissipated behaviors. And most important part will be these figures. The subsidence patterns, you can see that this is coast area, this is a mountain area. Okay, in the coast area, we can see the subsidence happen first. You can see that, okay? And then here in the central area, we see the subsidence second. Okay, so they match the original concept, original mechanism. We see that in this area, in the past, we see the subsidence mainly occur in the coastal area. And after that, they propagate to the central. So these kind of models, they look like they can represent these kind of behaviors. We see the subsidence in the coast first because their clay is relatively thin. The clay is relatively thin. You can see that the clay is very thin here. But this area, they become very thick. Your clay is relatively thick. So it takes much longer time to have dissipated. So the subsidence occurred in a coastal area. But after that, if you have the same decline of the head, this one will contribute much more than your coastal area. So initially, you have a compression in the coast, and then move to the central. Your central length subsidence hotspot move to the centrals. They demonstrate that your clay distributions or your geological distributions could be the reasons to induce this kind of shift of the subsidence pattern. Okay. That's quite interesting. I don't know, if others know that. Okay, so Another is we try to compare independent and dependent parameters. Independent means that the parameter is constant. They will not change with time or environment. And dependent parameter means that it will change with time. When your water stream occurred, your porosity decreased, your permeability decreased. So they also imply that your flow be decreased, your flow rate be decreased when your K decrease, right? And another part is that when your water stream occurred, you be compressed. That means your total matrix become more rigidity. Okay, and more rigidity means that your compression quantity will decrease. You are not able to compress largely. Your compression will become slow down. Okay, so there will be the total combined together. You can see that if you're using independent parameter, constant parameters, you will able to obtain larger subsidence quantities. But if you consider the dependent parameters, your subsidence quantity decrease largely, okay? And this one will be more approach to the reality because it should change, your porosity should change, your K should change, and your rigidity should be changed, okay? Not the constants. Yeah, just to demonstrate that. And here is to do some analysis. We have the different observation on the surface for the two models to do a comparison. And here is to assess the final subsidence time. Okay, model 4 is larger than model 3. So GSMMA take much more time to reach the steady state conditions or the final compression conditions. And WIA will reach the steady state quickly. The same condition, the same geologic conditions. Okay, so this is the different kind of result. Like a CGS models, we can see that they reach the steady state or final compressions take around 550 years. Okay, that means even we do not change any water levels, the conditions they reach the steady state need to have more than 500 years. That means if you do not do any work, you just stop pumping. Like right now we see the water levels the same, stable, okay? But you cannot solve the subsidence problem. Subsidence problem needs you have extra waters inside to increase the water level because the past is this level, right now it's this level. If you do not let your water levels approach to your original levels, they take 500 years to reach the final compression. Okay. So that means WIA, their strategy is incorrect. I tell them that you cannot just stop pumping. If you stop pumping, you cannot solve the problem. You need to have recharge. If you do not have recharge, you cannot solve the problems because they have residual the consolidation head there to continuously induce the problems. Yeah, this is just some of the results for your reference. But if you consider the time dependence, the stable condition will become quick, okay? Because they are not easy to be compressed. There will be more rigidity. So they become like around 300 years, like that. But your WIA models reach the steady state very quickly, 200 years. Okay, so they imply that your hydrogeological model affect largely for your result, for this then subsidence result. And if you consider more completely the geological model, you might be able to do the simulations more correctly, like the phenomena that we can observe the shift of the central of the subsidence. Okay, and this is final accumulation quantities. That could be around 3 meters. And if you're using a GSMMA model, that could be more than 3 meters. But if you consider like a dependent parameter, it will become 2 meters. Yeah, but this is based on the setting of the models, not based on the really parameter settings. If you're using a really parameter setting, I think the quantity will be larger. Because we found that the parameters, the compressibility of the parameters for the in situ data is much larger than we setting. we using like the gravels or the cross sense, the E values is relatively large. So they are not easy to be compressed. But for the reality in the data, that we found that even the aquifer system, they still have high compressibility. So that means that they might be relatively soft. And then the time to reach the steady state will be much longer time. And the quantity, the final displacement will be much larger than this. Okay, this is ideal case. It's not for the reality. Okay, so in these studies, geological model have significant impact on the assessment of the land subsidence. The hydrogeological model that conformed the local situations can reasonably assess the distribution of land subsidence. And another could be the coupled hydromechanical models is more reasonable to describing the behavior for land subsidence. Yeah, there's another. Okay, I don't know if you have any questions about this work. And following, we're using a similar concept, but we apply to different fields. So we're developing a couple hydromechanical chemical models to investigate the influences of geological model complexity in simulating seawater intrusion and land subsidence together. Okay, so this is done by right now he's a study PhD. And the content here is for the master thesis and published in Journal Hydrology. And very similar like Yonghan, but Yonghan, she do not write in the manuscript, so we do not publish that paper. Okay. So in the coast area, we know they'll be quite complex for the seawater and groundwater exchange or interactions. So they might have the seawater intrusion problems. We might have the submarine groundwater discharge because naturally this elevation is high, this elevation is lower. So the groundwater flow is from the land flow to the ocean. So we have commonly have gradually outflow patterns. We call the submarine groundwater discharge. And another, if you pump too much waters inland, you might induce the seawater intrusion. Okay, so they become like interactions. And another is due to the tidal variations. The system in the coast area is quite complex. That's very easy. When there's a high tide, the water will push in. When there's low tide, the water push out. Okay, so they continuously have the flow in, flow out patterns. Although the quantity is not larger, we using the like tide coast, we might have around 1.5 meter variations of the sea tide, and we see that the variation for the interface is around 1 meters. Okay, so the quantity is not very large. If they are stable conditions, they just like that. But if you have pumpings or have others, there will be larger differences. And in these models, we try to do the work like we have the pumpings. So as we know that the pumping will induce land subsidence. And in the coast area, when you have pumpings, you might easy to induce the seawater intrusions. Okay. And in the past, we found that they discussing the issue separately, but nobody try to combine them together for the simulation or for the assessment. So that means this kind of research become valuable because we are the first one to propose this model. And we use in the HMC, the water flow, and mechanical part is we call it polyelectricity systems. And another is we use the solute transport to simulate the seawater intrusions because they become like a solute. They have the high concentrations flow in and flow out. So we're using a solute transport to do the simulations. So we developed this HMC model to assess immediately for both the land subsidence and seawater intrusion issues together, and discussing the geological system, how it affected this kind of interaction behaviors. Okay, we take 10-minute break and go back.